All right, this is going to be the third part video for AP Statistics, chapters 14, 15, which are the foundational probability rules. And today we're going to talk about the compound and rules. So if you have one event and another event, and you define the probability of combining them together in and, one event and another event has to happen. And then we'll talk about the associated special case of that, which is called independent events. All right, let me share the screen here and we will get started. Okay, so we've talked about the OR event, and maybe I can just quickly run over that. When we have OR, well, what have we covered so far? Just to kind of put it in perspective. We know that if we have a probability of some event E, then that's called a simple probability. And that's where the sample space, the entire sample space, forms the bottom of the fraction. And then there's some event inside there that forms the top of the fraction, right? So you have some number, either they're a probability or a count typically out of the entire total. And then we described the probability of an event given some sort of condition. That's called a conditional probability. And the idea there is you still have a fraction, you have a population, right? But you've imposed a condition first. And so you're taking a subset of the population that's defined by what's after the line. And then you're looking at the probability inside that meets the criteria for being in the event, right? And then we talked about what if we have two events? So we have an event A and we have an event B. So for example, we have two events like A and B like this in some sort of sample space. And we want to find the probability of A or B, right, which we said we would write this way with a union symbol. And we found out that OR is equal to add, right? So you'd take the probability of A and you'd add the probability of B, but you don't want to double count the stuff in the middle, so you have to subtract off the probability of A and B, right? This symbol here is and, so that you don't double count the middle, right? And then we said there's a special case, right? The special case for OR is when the two events do not connect, right? The name for this is disjoint events because they have no joint probability, or also known as mutually exclusive. And when that's true, the probability of A and B occurring together is 0. So this goes away and you end up with a simpler version of the formula. The probability of A or B is just the probability of A plus the probability of B, period. All right, so that's where we've been so far in probability. Now we're going to add on, what if we have these two events, but it's one event and another event, and we're going to switch to a different way to picture. We're going to talk about a tree at a certain point. Okay, let's just introduce it with that same table of data. Let's say that we have choices about entertainment, reading a book, playing video games, or watching Netflix as their favorite choice for a set of students that are separated by into genders, girl and boy. And maybe we would want to ask a question here. To find the probability that a chosen student is a girl and prefers to read a book, right? We could do that by considering that to be just one event, not considering that to be two separate events, girl and book, but girl and book as a single event. And that means we would be taking out of the entire sample space, which is all 100 students, we would have to look for all the people that are both girls and they also read a book. And that would be this 18 students here. So it's 18 out of 100, or 18%. And we know for sure that's correct. But it would be interesting to see if we could deal with the probability of girl and the probability of book separately and combine them in some way to get this, okay? All right, so by the way, the reason why the and symbol is written this way is because this is the set notation for intersection. And you can see how now why that 18 is the intersection of the read a book row and the girls column. Okay. All right. So if you think about this, right, how can we combine these separate probabilities of girl and boy in some way, right? Well, the probability of just being a girl would be 60 out of 100, which is 60%. And the probability of someone liking a book would be 22 out of 100, or 22%, right? In the OR case, there was more than one way for something to get in the event. They could be in the event with just A, or just B, or both of them. So it made sense that we added because the probabilities increase when we add probabilities. Here, it's more exclusive. To be in this group, right, there's a 60% chance of being a girl. There's a 22% chance of liking a book. But to be in both at the same time is even more exclusive. So that should result in a smaller probability, right? But if we add probabilities, we always get bigger. But since these are basically fractions, anytime you multiply a fraction by a fraction that's less than 1, you end up getting smaller. So this suggests that maybe for and we should multiply. In fact, the rule might be, and in fact is, and is multiply probabilities. Okay, so let's just try that. What would happen if we just multiplied the probability? So the probability of a girl here, right, this would be 60 out of 100 people are girls, and 22 out of 100 people read a book. And if you multiply those two things together, you get, let's see, 60 out of 100 times 22 out of 100. That gives you 0.132, or 13.2%. But that does not match what we know to be true. In the previous screen, we know that the actual probability is 18%. So why did that not work? Well, the reason it didn't work is there's a catch. And is multiply, but the catch is that when we have to be in both of these things. When I computed the second one here, the book, right, I used this number, 22 out of 100. And that 22 included girls, but it also included boys. And so these 4 people here really shouldn't have been included because they're not and a girl, right? So the catch is that whenever you do probabilities, you have to adjust the second probability to also include the fact that the first one occurred, right? We're going to make that second probability a conditional probability. So we're going to say the first probability is the probability that you can pick either of the events. We'll pick girl, find the probability of being a girl, which is 60 out of 100 here. But then when you multiply by the second probability, we're going to find the probability of liking a book. We're going to stick to the girls. So we're going to say, what's the conditional probability of liking a book given that you meet the condition that you're a girl? And so that would not be 22 out of 100. That would be 18 out of 60. So the second probability has to be a conditional probability. And then when you multiply, these 60s cross out, and we indeed get 18 out of 100, which is correct. So the catch is, and is multiply, but the second probability has to be conditional and take into account that the first event happened. Okay, it's kind of like this. The best way to see it, I think, at this point is, if you're drawing 2 cards out of a deck, and let's say that we want to find the probability that the first one's a queen and the second one's a queen. I think from earlier courses in probability, if we know that there are 4 queens in the deck out of 52, and we know that and is multiply, it seems like we should then multiply by the probability of the second one being a queen. But when we can compute that one, we have to realize that the first queen has been removed. So now there's 51 cards in the deck, and only 3 of those are left. Those are queens. So this one is the probability that the first one's a queen. But this one is the probability that the second one is a queen, given that the first one was a queen. And therefore, it's a conditional probability, right? That always has to occur. That when you calculate the second probability, you have to think about what happened first and account for that. Okay? Right. So we used a Venn diagram when we pictured the OR case, because that's a good way to combine summing probabilities. The best way to visualize this is with this structure, which is called a tree diagram. So a tree diagram assumes that the events happen in a sequence. And this can be used even when the events don't literally happen in a sequence. But you can pick one of the events, like say the gender, right? And the 2 possibilities here are girl or boy. So there's some probability that the person we pick is a girl, and some probability that the person we pick is a boy. But then if we pick a girl, we're here at the tree, then there's 3 choices that we could have had for the entertainment choice: book, games, and Netflix. And that means the second line here is a conditional probability. This is the probability that somebody likes a book, but given that they're a girl. The probability somebody likes games, given that they're a girl. The probability of Netflix, given a girl. And down here, these are all the conditional probabilities for the condition boy. So given that they're a boy, do they like book, games, or Netflix? So for us to find the probability that somebody is a girl, and that's it, simple as and, they like to read a book, we have to traverse this tree to the end, right? First, we have to say, okay, they're a girl. That's the probability that they're a girl. And then we have to say, okay, now that they're here, what's the probability that they take that particular path? So we're going to multiply by the probability that they like book, given that they're a girl. Okay, to get finally to this location here. So these probabilities at the end of the tree are and probabilities. Girl and book, girl and games, girl and Netflix, boy and book, boy and games, boy and Netflix. Right? So the first ones are simple probabilities, the second ones are conditional probabilities, and the third ones are and probabilities. Okay, so the reason why I like that structure is that for me, if you just look at the top of a branch, it helps you to recreate the formula that you need. If you remember that you multiply as you go across the events in a tree. And this could be extended to any number of events, but for now we're just taking two. So if you say, all right, we want to get out here, then first you pick one of these things, probability of girl, and then the second one is the probability of the other one given that the girl happened. Book given girl in this case, right? So in our tree we could have reversed this, right? There's no particular reason we had to start with the event girl. We could have started with the event books, games, and Netflix, and then the second part of the tree would have been reversed. Then we would this line here would be the probability of girl given book and boy given book, girl given games, boy given games. And so to get to that same spot, it could have been, what's the probability that somebody likes a book? And then what's the probability that they're a girl given that they like to book? And both of those things, so this and this have to happen to get out here, girl and book. All right. Right, so that means there's actually two ways to get to that spot out there, right? You could say it's the probability of being a girl times the probability of liking books given that you're a girl, or it's the probability of somebody liking books times the probability of being a girl given that you like a book. Either of those ways would be the correct way to compute this, okay? Right, just to show that, let's show these two things. So let's do this first one. I'll do this one here in blue, right? The probability of being a girl would be 60 out of 100, right? And then the probability of book given girl, if you're staying within girl, right? Book given girl would be 18 out of 60. These would cancel and you would end up getting 18 out of 100, right? But we could also instead have said, all right, what if we decided to do this one? Well, that's the probability of book, and book is 22 out of 100, right? And then what's the probability of girl given book, right? So given that you're a book, right, it would be probability of girl given book, which is 18 out of 22. And these 22s would cancel when we multiply here, so we would again get 18 out of 100. So it doesn't matter which event you put first, as long as you account for that event when you compute the second conditional probability. All right, so the way I remember this formula is for and is these are the general formulas that work in all cases. Is I just draw out the top branch of a tree and I say, let's imagine, well, I'll draw the entire tree here. Okay, actually, I'll do the rest of this in green. Okay, so this is B. And then I've got, actually, let me back up here. Okay. So this is A, and this is the fact that A does not happen. This is the probability of some other event B happening, and this would be that B does not happen. This would be B happening and B not happening. So this would be all the ways that two things can account. They both happen, one but not the other one but not this one, and then neither of them happen. Right? But if you just picture that top of the tree, imagine that you're writing probabilities. This is the probability of A happening. And then this would be the probability that B happens given that A happens. And then out here, this would be the probability of A and B happening. And therefore, that's equal to the probability of A times the probability of B given A. So in my mind, I picture this top branch of this tree to recall this formula. The probability of A and B, the intersection, is the probability of A times the probability of B, or we could have reversed the order here. It's also the probability of B times the probability of A given that B happened. That works in all cases, okay? So it is that and is multiply, but the catch is that one of the probabilities has to be a conditional probability. Okay. Now in the OR case, we found that there was a special case, which was that if the events were disjoint or mutually exclusive, then that simplified the case, and we got a simplified OR case because disjoint events have no overlap to subtract. There's also a special case here in the and situations, and that's if the events are independent of each other. Okay, so we'll define that to be this. Events are independent if the probability of one event does not change if the other event happens or doesn't happen. So it doesn't matter what the other event happens, whether it happens or not, the probability of the first event is unaffected, it's independent. Okay, so let's look at two cases side by side here. I'm going to look at the more general case, and then we'll look at the special case of independent events. So I've made up two different versions of the table here, two different data. Here's our original table. Okay, and if we were to compute out this whole tree with gender first and then entertainment choice, right, there's 6 out of 100, so 60% chance of someone being a girl, 40% boy. And then given in the girls column here, this for example, this probability of boy given or book given girl is 18 out of 60. That turns out to be 30%. So these are all from this table. Okay. And so if I wanted to find, for example, the probability of games, given that somebody's a girl, then I would say, all right, the girls are 60 here, right? And out of the 60, 12 of them are games, right? So that's 20%. And then if I wanted to compute in another column, what's the probability of games? Again, another way to calculate probability of games, but this time given a different condition, given that we're talking about the boys, right? Then that would be 20 out of 40. And that would be 50%. And that means that the probability of someone liking games is changing depending upon the gender, right? In other words, girls have a 20% chance of liking games, right? In this column, games are 20%. But in the boys column, games are 50%. That implies that liking games depends upon gender, because more boys like games than girls in this data, okay? Now, this table over here has been adjusted so that it's independent, so I can show you what that looks like. This is the corresponding tree if you want to all work it out, okay? And I'll do that same thing. I'm gonna find, let's pick an event like games and find two ways to compute it. So I'll use the same color scheme. The probability of games given that you're a girl in this data set is there are 60 girls and 30 of them like games. 30 out of 60 is 50%. But then if you consider just the boys and find the conditional probability that they like games, 20 out of 40 is also 50%. And that means the probability of liking games stays 50%, regardless of whether the person is a girl or a boy. It seems to be independent of gender. So we would say that the probability of liking games is independent of gender. Okay, on a tree, what that looks like is for independent events, these conditional probabilities, they're exactly the same for the same choice, regardless of which branch we took first. Whereas over here, these do not match. And this is the more general case. Usually events depend on each other in some way. Kind of like in the OR case, there's usually overlap, right? But the special case for AND is called independent events, okay? So just like we had OR special cases disjoint, for AND special cases independent. And that should result in a simplified version of the formula. So let's take a look at the formula real quick. Well, let's do one more thing. Here's another way to visualize this, just to connect to something from Unit 1. You remember before we said that events are independent if the percentages are staying the same across the different bars. If we used a segmented bar graph to show the percentage of people that like games and don't choose games as their best, their favorite option, in the non-independent case over here, we would have that, let's say 12 out of 60% or 20% of people chose games in the girls, right? But 20 out of 40, which is 50%, chose for the boys. And since these are larger than 15% difference, we would say that these are not independent of each other, that one depends on the other, right? So this connects to that same idea from Unit 1, that there's a dependency if the percentages are changing. Over here, for the case where they're independent, then that means the probability of somebody liking games is staying the same percentage all the way across for the independent case, okay? Now, the one thing that's different here is back in Unit 1, we said that as long as these percentages were about the same, like within 15%, we said that we could call those things independent. When we're doing probability calculations, it's more stricter than that. These probabilities have to be exactly the same for us to declare something independent. If there's any difference at all, then we say there is a dependency. It's the same idea, but it's a little stricter when it comes to probability calculations. All right. So how would we test for independence? Well, what we do is we pick an event, like say games, and then we find two of the three ways to calculate it. Okay, we could compute the probability of games given that you're a girl, or given that you're not a girl. Okay, and then we compute those to see if they're the same. If they're both, say, some like 40% and 40%, they're the same, then we say they're independent. If there's any difference, we say they're not independent. And I want to point out that there's a third way to calculate the probability of games. We could also figure out, so this is, say, the probability of games given girl, and this would be the probability of games given not girl, which in this case was boy. What would this one be? This would be just the probability of games, period. So what would that look like if I go back to a table over here, right? The probability here, well, I'll take the one which is independent. So this was 30 out of 60, 20 out of 40. So the probability of just liking games, period, means you don't consider the condition at all. You just consider the entire table. Well, that's these numbers out of here, 50 out of 100. And so the third way to compute the probability of games is just to ignore the condition, the gender completely, and just find the probability of games players for the entire table, 50 out of 100. And so what will happen here is all three of these will match, like say 40, 40, 40, or 50, 50, 50 in that case. I just don't want to imply it has to be 50%. Or they will all be different. Like if this is 20 and this is 40, this one would be something like 30, somewhere in between the other two. So they're either all going to match or they're all not going to match. So you don't actually have to find all three. You can pick any two of these events and find the probability. Check any two of the three ways to find the probability of one of the events. It doesn't matter which one. If they don't match, then that means they're independent. Okay. So for example, let me show you another case. I wouldn't have had to pick games. Let me take a table here from back here, and we'll just test it a different way. So let me see if I can grab just that. Yeah, okay. Let's say that I wanted to, with this data, test whether or not, now we're really testing two variables, right? We're testing whether entertainment choice is independent of gender, okay? So what I could do is pick one of the events, one of the values. It doesn't matter what. I'm going to pick this, probability of boys. I'll just pick one event of gender. And then I'm going to try to find multiple ways to calculate that. So let's find the probability that somebody is a boy. And then let's find the probability that somebody is a boy given that they like Netflix. Okay. If entertainment, or if gender is independent of entertainment choice, then that means that no matter what way I decide to compute the probability of being a boy, it would have to be the same. The question is, are these probabilities equal? So let's find the probability of boy. That's a simple probability. And so that means out of all 100 students here, the boys are 40. So it's 40 out of 100. So there's a 40% chance that a student at random would be a boy. Another way to find the probability of boy would be to restrict ourselves to the Netflix group. So out of the 46 people in the Netflix group, 16 of those were boys. So that's a conditional probability of boy given Netflix, and 16 out of 46 turns out to be 0.3478. Because these two things do not match, that means the probability of boy is changing depending upon what I think about the entertainment choice. So we'd have to say gender depends on entertainment, right? Actually, it's not going to change. It would probably be better to write that the other way around. Entertainment choice depends on gender. Okay, so that's the idea. Pick one value of one variable and find two different ways to compute it. Now I could have done boy given book compared to boy given games. As long as they match, then that means they're independent. If they don't match, they aren't. So that's our test for independence. And if we find that something is the special case of independence, it's going to simplify the formula. Here's the AND formula, right? We know that the probability of A and B is equal to the probability of A times the probability of B, given that A happens. The second one has to be conditional. That was the catch for AND. But if the events are independent events, then that means the probability of B is not changing. So the probability of B would be the same as the probability of B if we know A happens, and would be the probability of B if we know A doesn't happen. And that means that we get to replace this one with the more simple version, probability of B. So we get a simplified version in the special case of AND, independent events. When we have independent events, we get the simpler version where we don't have to have a conditional probability there. Okay? And so for some reason, a lot of books, well, I understand the reason why, they will say that the test for independence is not to see whether the probability of one thing is changing. It's to look at the special case formula where this is an independent and see if it's true. Because the only way the special case formula is true is if these are independent. So if you are really great at recalling your probability lessons from earlier, like in Algebra 2 or Honors Algebra 2, they probably said this is the test for independence, right? And that's the reason why. But to me, it's more of a consequence of independence. What really makes something independent conceptually is that the probability of one of the events is not changing, regardless of if I consider the other event. All right. So I picture a tree, right? You can put A first and B. Probability of A and B is probability of A times probability of B given A, or they can be swapped. The probability of A and B is the probability of B times the probability of A given B. Okay? And then just to compare that for OR, just to kind of tie this up, for OR, I picture a Venn diagram, right? The general case is if they overlap. So if I have A, B, I think the probability of A or B is the probability of A plus the probability of B, and then minus the overlap of A and B. And then the special case over here is disjoint events, also known as mutually exclusive events, and that's when the probability of A and B equals 0. So we get the simpler form. A or B is just the probability of A plus the probability of B, and you don't have to subtract anything. So we have the OR formula and its special case. You have the AND formula and its special case, right? This one. Actually, this formula. And then you have the idea of conditional probability. Those 5 things there are the foundation of probability. If you understand how those 5 things work, you can solve any probability problem. Sometimes it's easy, sometimes it's hard, but every problem can be solved in some way with those formulas. All right, at this point, we can actually do problems 10 and 11. So let's go ahead and work on 10 and 11. I'll have you suggest you pause the video and then go ahead and unpause and I'll show the solutions. Okay, this first one, we actually did some of this before in the earlier part, but we'll repeat it just for to kind of tie points together here. So if you have a table here that shows whether people favor or oppose the death penalty, and you have the data broken out by political party, Republican, Democrat, or other, we could answer various questions. A says, find the probability that a randomly chosen voter favors the death penalty. So that would be probability of favoring, and we're not saying anything about party. So this is a simple probability. So we're taking the entire table, and then we're considering just the people that favor the death penalty, which is all of these. So that means that the bottom is going to be the sum of all these numbers, 0.26, 0.12, 0.24, 0.04, 0.24, 0.1. And the reason I'm able to add is really I'm doing OR. This or this or this or this, OR is add. But we don't have to subtract an overlap because in a sample space listing, all of these are mutually exclusive, right? And there's no overlap. And then we would want just the favor ones, which is 0.26, 0.12, and 0.24. So that turns out to be, this is out of 100% because we're talking probabilities in here. They'll always add to 100. 0.26 plus 0.12 plus 0.24 turns out to be 62. And so we have a 62% chance of picking somebody who is favoring the death penalty. That's part A, simple probability. Part B says find the probability that a Republican favors the death penalty. Favors the death penalty, I think, is is what we're finding the probability of, and this wording suggests that being a Republican is a condition. So we want to say just considering the Republicans. So we want probability of being favoring the death penalty given that you're Republican. So that means that we're not going to have the entire table. We're going to have just the Republicans. So that would be this portion, the 0.26 plus 0.04. But then we're going to be saying how many people favor. So within that, the 0.26 out of that. So 0.26 out of 0.30, right? So 0.26 divided by 0.3 turns out to be 0.87. So there's an 87% chance that given you're a Republican, you favor the death penalty. Okay. And then the next one would be find the probability that a voter who favors the death penalty is a Democrat. So this seems to be favoring the death penalty is now the condition. So we want to say, what's the probability that you're a Democrat given that you favor the death penalty? So now we're talking about a conditional probability, and we're talking about the condition now is favoring the death penalty. So that would be out of these people. Out of the people who favored the death penalty, which turns out to be 62%, the answer from A, then what is the probability that you're a Democrat? That would be the 12. So by doing it this way, hopefully I'm emphasizing to you that you can compute any probability as a fraction. The bottom is the sample space. It's either the entire sample space or it's a conditional sample space. And then the numerator is just always within that sample space what meets the event criteria, right? So 12 out of 62 would be 19%, okay? Okay, so we did that much before. Now let's go on to the new ones here. D, a candidate, so it says a candidate thinks they have a good chance of gaining votes of anyone who is a Republican or in favor of the death penalty. What proportion of voters is that? So this is an or probability. You want the probability of being a Republican or favoring the death penalty, okay? Okay, I'm going to do this with the formula, but I'll also show this on that table. So that would be the probability that somebody is a Republican plus the probability that they favor the Democrat or they favor the death penalty, but minus the probability that they're both at the same time Republican and favor the death penalty, because we don't want to count those people twice. So the probability of being a Republican would be the Republicans out of the total, right? So that's going to be 0.26 plus 0.01 out of the entire amount, right? Which turns out to be 30%. Okay, so 30% Republicans plus the probability of favoring the death penalty would be, all right, so now we're talking about the favor people, right? That turns out to be, let's see, the 0.26 plus 0.12 plus 0.24 out of the 100%, which is 62%. So if I just add them up, Republicans and also the favoring, I'm going to get 92%. But that's a little too high because these people that were at this intersection here got counted twice. So we're going to subtract off the probability that they are Republicans and favor, right? And so that's, again, a simple probability. It's out of the entire table, right? So out of 1, but they have to be in here. We have to be Republican, so in this row, and favor. So it's just this 0.26. So we would subtract off 0.26. So we're going to add up the 30% plus the 0.262 minus the 0.26, and we'll get 66%. So there's a 66% chance that they're Republican and also favor the death penalty, okay? Now, the other way to do this without using the formula would be to just go to the table and consider the whole thing to be, so I'll use a different color here, but carefully consider every one of these and make sure that they meet, that they are Republican or they favor the death penalty. Which ones do I include? I would include this one and this one because this gets in there because of the Republican part, right? And then this one because it gets in there because of the favor part, and this one here, right? So this would be people who are Republicans or favor or both. And then you could add up those numbers, right? If I added up 0.26 plus 0.12 plus 0.24 plus 0.04, I'm going to get the same 66%. So you either have to think of it as a simple probability and carefully consider every single thing, or you can break this into separate events, but when you add them, you have to subtract off the overlap so it doesn't get counted twice. All right, so then let's go ahead and look at the last question there. I'm just going to erase all this. And we'll answer the question, is party affiliation dependent on and a death penalty favoring, are they independent? In other words, we want to know, is this variable and this variable, are there the dependency? So what I'm going to do is I'm going to pick one of these cases here. Like let's use Republican. So I'm going to find two different ways to calculate Republican. Okay, there's actually three ways I could calculate it. I could find probability of someone being a Republican, probability of them being a Republican given that they favor the death penalty, or probability that they're Republican given that they oppose. And I can pick any two. It doesn't matter which two. Let's pick this one, and we'll just calculate those to see if the probability of Republican is changing. So what's the probability of Republican? Well, that is a simple probability out of the entire table. So that's going to be out of the whole 100%, 26 plus 0.04 is 30%. There's a 30% chance that someone from this group is a Republican. This one is a conditional probability. So the bottom of the fraction is going to only be the ones that meet the condition that they oppose. So that would be this group here, 0.04 plus 0.24 plus 0.10, 0.04 plus 0.24 plus 0.1. That turns out to be 38%. And then within that, what's the probability that they're a Republican? That's 0.04. And so 0.04 divided by 0.38 is about 11%. Okay, so because these two things do not match, it means the probability of being a Republican in this group is changing depending upon what I know about them for their favoring the death penalty. And that means these are not independent. Okay, the way I like to write that is this. I would say favoring the death penalty depends upon party. Okay, there is a dependency. Okay, but here we're talking about the entire favoring the death penalty variable is not independent of the entire party variable. To test it though, I just need to pick one value of one of them. I just happen to pick Republican, and then find multiple ways to compute that probability. All right, so that's that problem. Let's take a look at this last one, and then that'll wrap up this video. And we have one more video to cover these foundational things. Okay, if you draw a card at random from a standard deck of 52 cards, what's the probability that it's a heart given that it's red? All right, well, I could use a picture of this. Maybe I can grab a picture from earlier in here and just put that on the other page so that I can quickly go back and forth. Somewhere in here I had a picture of, there it is, of a card deck. So can I get that? Yep, let's grab that and jump up here so that I can quickly kind of combine. It's been helpful to have the sample space listed out, and I think this will continue to be true. So let's have that available to us. All right. What's the probability that a card is a heart given that it's red? So I'm going to write that out. I always like writing this probability statement, heart given that it's red, because that helps me determine that the bottom of the fraction is going to be all the red. So I would go to a thing here and say how many. I could count these, right? There's 52. There's 13 in each of these rows. So 13 and 13 more is a total of 26 red cards. So there's 26 red cards. And then inside that red card sample space, how many of those are hearts? Well, the hearts are just this. So it'd be this 13 out of the 26, right? So 13 out of 26 is 52%. Okay. All right. Part B would be, what's the probability that a card is red given that it's a heart? Okay. So hearts are 13 of the cards. So the bottom of the fraction here will be 13. And then within the hearts, how many of those are red? Well, all of the hearts are red, so all 13. Right? So there's a 100% chance. If I know that I have a heart, there's a 100% chance that it's a red card. All right. And then C, what's the probability that a card is an ace given that it's red? Okay, so there are 26 red cards. How many of those red cards are aces? So in these red cards, 2 of them are aces, right? So it's going to be 2 out of the 26. So you could just write it that way, or if you wanted to simplify the fraction, 1 out of 13, right? Or you could write it as a percentage, or like as a decimal. 0.0769, or you could write it as 7.7%. These are all valid ways to write it. Unsimplified fraction, simplified fraction, decimal percentage. All right, and then the last one here is what's the probability that a card is a queen given that it's a face card? Okay, so how many face cards are in the deck? Well, that's all the ones with faces. There's 3, 6, 9, 12 face cards. There's 12 face cards. How many of those are queens? So staying inside the face cards, 4 of those are queens. So that's going to be 4 out of 12, or 1/3. Okay. All right. So sample space listing, a great way to do something. Whether you've got the whole sample space listed, or a tree, or a Venn diagram, then you can use that to figure out the portion that's in the denominator, and staying within that portion, which portion do I include on the top. All right, that's going to wrap up this video. We have one more to cover.